hopefully this would provide some revenue for the plant. Currently, the plant has a gravity thickener, and the sludge is taken away from the plant into sludge drying beds, where it is then taken away as Class B biosolids by a local farmer. We propose, with our improved design, that a belt thickener be added before the digesters to increase the rate at which solids are added, and also to construct a biosolids management building where to help reduce odors and septic conditions. This inside the building will be a belt filter press where the sludge is dewatered and prepared for composting. After this process, wood chips will be added as a bulking agent and placed into windrows in the existing sludge drying beds. It is here where the compost rows will be monitored to meet Class A requirements. And once those requirements have been met, we pass through a trommel screen to remove the bulking agent. In the summer months, we can apply this to our agricultural land for the plant's nutrients and also to prevent land loss. In the winter, we can bag it and sell it to the public as Davy Code premium compost. So energy recovery has been becoming more popular and successful as technology improves. There are many examples along the East Coast and in Europe where this has been proven a worthwhile venture. One problem with energy production is the presence of siloxanes in biogas. So we propose that an improved filtration system be added to the plant, and then the plant could possibly use biofuel to fuel county vehicles and utility trucks, buses, or we could also use it as a combined heating heat and power generation process where we get electricity from turbine generators and also can provide heating and cooling to the facilities. Now let me turn the time over to Ayman so he can tell you about the economic merits of our alternatives and the way forward for South Davis.
Yeah, thank you, Chris. All right, so here's the fun part in our presentation. So we looked into all the options that Ali has explained in terms of the total phosphorus treatment, and then we designed some technical and merit criteria, technical and economic criteria that we evaluated those options against. In the technical part, we looked into the reliability of those options in terms of their ability to handle fluctuation in flow and high loads of phosphorus. We looked into the recovery potential of these options. We also looked into, we factored in the input and some input we got from the district, and also we looked into the compatibility with the existing system, and finally the ease of operation. And in terms of the economic analysis for those options, we looked into the capital and O&M cost, and we factored that in to calculate the cost per connection. In terms of how those options were scored, we scored each one of the three options, adding more dose, the chemical options, or the mineral adsorption, and the biological options. We scored them technically for those technical criteria on a score from 1 to 5, and we use the weighting factor to help add more weight to the things that we think more important. And with that, the technical analysis, the chemical option scored the lowest in terms of because of its lowest reliability in meeting high loads of phosphorus, and also because the phosphate sludge that will go into digesters will release phosphorus back in the system, and will cycle that back to the headworks as part of the filtrate that will go in the dewatering process, which means that will require adding more chemicals to the system and accumulating phosphorus, which added the uncertainty. Also, this option scored low because of the increased sludge production that's associated with the chemical addition. In terms of the